Hello, and welcome to this unit on robotics fundamentals. Before we begin, I wanted to give you an idea of what the basic theme of this module will be about. Our goal here is to provide you with the mathematical tools that we're going to need to talk about where things are in space. Now, this sounds like a relatively simple task, and it is, but there are a few subtleties that we're going to need to get right in order to get our thinking clear, and so that we'll ultimately be able to write code to guide various robots. To motivate this problem, imagine that you're trying to program a humanoid robot like this one to pick up a cup. You may start by developing a system to locate the cup with respect to the camera system, which is embedded in the head of the robot. Now, you may also be interested in figuring out where that cup is with respect to the gripper that you're going to be using to actually manipulate the object. Both of these perspectives are important, and we need to be able to relate them in our thinking and in the code that we will ultimately write. Now, one of the basic tools that we're going to be using to talk about where things are goes all the way back to Descartes. He proposed this idea of a Cartesian coordinate frame of reference. Here we're depicting this in the plane. The basic idea is pretty simple. We start with a Cartesian frame of reference, depicted here by these two axes, x and y, and an implicit origin right here. Once we've established this coordinate frame of reference, we can talk about the location of points in the plane by associating them with tuples, denoting their coordinates with respect to this frame of reference. Note that we could also use this kind of representation to talk about vectors corresponding to directions in the plane or displacements. Here, for instance, we can think of a displacement vector, which is represented by this tuple, indicating a displacement of 1 unit along the x-axis and 3 units along the y-axis. Let's call these tuples of numbers, stacked up vertically, vectors. Here we're showing an example, a vector v, associated with this tuple here, 2, 1. We will say that v is an element of R2 to denote the fact that it's composed of 2 real numbers as opposed to, say, 2 complex numbers. We'll have more to say about vectors in this form in subsequent modules. Given this representation, it is natural to imagine simple algebraic operations like multiplication by a scalar or addition. In the first example, we can imagine a vector, 1, 2, being multiplied by a scalar, in this case, 5. The operation proceeds by simply multiplying each of the elements in that vector in turn by the scalar 5. In this case, the result would be a new tuple, 5, 10, where the first entry is simply 5 times 1, and the second is 5 times 2. Another operation that we can imagine is addition. Here we have 2 vectors, 3, 7, and minus 5, 2, and the sum of those 2 vectors corresponds to this third result, minus 2, 9, where here again, the first element, minus 2, is the sum of 3 and minus 5, and the second element is a sum of 7 and 2. Basically, we're simply adding corresponding elements in the vector together. Now, we can actually place a kind of geometric interpretation on these algebraic operations. Here, for instance, if we think of each of these tuples as corresponding to a vector in space, scalar multiplication corresponds to scaling a vector by that amount. So here we can imagine starting with an initial vector v and scaling it by a factor a, which corresponds to scalar multiplication, and getting a new vector, a times v. Similarly, we can imagine 2 vectors, v and w, represented by tuples in the plane consisting of 2 numbers, and think of their algebraic sum as corresponding to a new vector, which represents the result of adding these 2 vectors head to tail. Note that there's nothing special about the number 2 here, other than the fact that elements of R2 correspond very naturally to points in the Cartesian plane. we could equally easily talk about points in R3, like so. Here we're talking about tuples composed of 3 real numbers. Equivalently, we could be talking about tuples consisting of 6 numbers. In this case, this would be depicted by R6. R again corresponding to real numbers, and the exponent 6 corresponding to the number of elements in the tuple. In general, when talking about a set Rn, the number n denotes the dimension of the vector. We will also be interested in talking about the locations of objects in 3-dimensional space. Here, the vector space R3 will be particularly helpful. Here, we can imagine a coordinate frame consisting of 3 orthogonal axes, x, y, and z. And we can talk about the coordinates of a point by associating them with a triple of numbers, denoting the coordinates of that point along each of these 3 orthogonal directions.